Welcome to EDU World Space.
So we have a gamma ray here emitted from a nucleus during radioactive decay, and it has an energy of 320 kilo electron volt. And we have to find the wavelength of the gamma ray. So we use equation 27.4 here to find the wavelength. So this equation says lambda is equal to c is the speed of light and f is the frequency, and this implies e our f, the frequency, is equal to e over h, and so lambda is equal to hc over e. Now before applying the equation, we need to convert our energy from electron volts to joules. So should be Hc over, so 1 electron volt is equal to 1.6 times 10 to the power minus 19 joules. So 320 electron volt will be 1.6 times 10 to the power minus 19 times 320 into 10 to the power 3. 10 to the power 3 comes from the kilo here, and this much joules. H is the Planck's constant and c is the speed of light. So when we do the calculation now, we get our lambda to be 3.88 times 10 to the power minus 12 meter, or we can say this is nearly equal to 3.9 times 10 to the power minus 3 nanometer. So this is the wavelength of the gamma ray, which has an energy of 320 kilo electron volt. Now now there is a second part of the question which asks us that whether or not there will be significant diffraction of this type of light, that means of a light of this much wavelength, when it passes through an everyday opening like a door. Now we know that significant diffraction will only occur when the opening is of the order of the wavelength. Now the opening of the door, or the breadth of the door, let's call this A, is of the order of like 1 meter. Now we can see that A is very greater than the wavelength of the gamma ray here. That means they are not of the same order at all. So this means there will be no significant diffraction through the doorway.